All right, guys, so today we're working on Objective 6.3c. We're going to finish up just our basic logarithms with graphing. Logarithms. Okay, thank you. Okay, and your instructional objective today, you will be successful. You can measure your success if you can graph a parent function of a log. And then you can use either a table of values or transformations to graph other logs. I am going to challenge you to use your transformations when it comes to graphing logarithms. So what is critical to remember? Here's the thing. Logs, if you recall, I've told you before, are inverses of exponents. So the graph of a log is a reflection of a graph of the exponent with the same base across y equals x. So when we have an exponential, y equals b to the x. So this is an exponential form, or an exponential function. If I wrote it f of x, you know it would be in function form, but it's still a graph. We typically graph three points. We pick -1, 0, and 1 for our x, and we plug them in. So we graph these points. We pick -1, and we get 1 over the base, whatever the base is, and we graph that point. Then we plug in 0 for x, and b to the 0 is 1. And then we plug in 1 for x, and we get the base 0. So typically when we're graphing just a basic exponential, those are the 3 points that we choose to graph. Now, I just told you that logs are inverses of exponents. That means their x's and y's switch. So if I say that I want you to graph y equals the log base b of x, really what I'm asking you to graph is the conversion of that, which is b to the y equals x, if we convert it to the exponential so that we can plug it into a table of values. So do you see what happened? The x's and y's switched. So in this case, I'd be picking values for y instead of values for x. So, right? Doesn't that make sense? So if I pick a value for y, so I'm looking at this right here, I'm picking a value for y, I would pick -1. And b to the -1 is 1 over the base, whatever it is. I would pick for y 0. b to the 0 is 1. I would pick y equals 1, and b to the 1 is b. So I don't know if you can see it. I'm hoping you're catching what's happening here. The x's and the y's are just switching spots. So let's go back to the exponential. What is my domain? Do I have a restriction, or can I put anything I want in position of x? Anything. So my domain is completely unrestricted, which for my inverse, my log, let's think about it. Can I put anything I want for y? I can, but that doesn't mean I can just get anything out that I want. So let's go back to the exponential. What's my range restriction? We always draw a horizontal asymptote here. 0 to infinity, because it doesn't matter what exponent I plug in. If I plug in b to the -1 million, that's 1 over b to the 1 million, which is tiny, but it's positive, and it's not 0. So that's our range. Same thing applies over here, but now our domain is restricted. So here we get a horizontal asymptote of y equals 0 because our range is restricted. Over here, we get a vertical asymptote because our domain is restricted. So x equals 0. So we can approach x equals 0, but we can't cross x equals 0. So everything I'm doing right here is just showing you that logs and exponentials are inverses of each other. Okay? And then just remember these little rules. B has to be positive, and it cannot equal 1. Okay? So remember that. So I'm just giving you a generalized statement where we can today choose to graph this set of points when we're graphing a logarithm. Or you can convert it to an exponential if you choose, and you can make a table of values. I'm okay with either one, but I am going to challenge you to choose to do the transformations with these sets of points because it'll be a lot faster. So in this case, we would pick negative 1, 0, and 1, and we would get 1 over the base, 1, 0, and base 1 if we were doing it in exponential form. Okay? Table of values, or just use that set of points and use some transformations. Okay, so I'm going to use a different color so we can just talk about transformation form of a logarithm. So here's if we have f of x is equal to a log base b of, I'm going to put a number in the coefficient. So I guess I'll put c times x minus d plus e. So I'm just plugging different values in, and I'm using b as my base for my logarithm. So these are transformational form. And guys, every time we do transformational form, these numbers outside that are not grouped with the x are what kind of actions? Vertical, right? So this is an example of a vertical stretch or compression. So I'm just going to put dilation to cover both of them, and also could be a vertical reflection or a flip. If it's negative, right? If it's a negative a, you flip it. Okay? And then if it's greater than 1, you stretch it, and if it's less than 1, you compress it. So remember that. So that's A. And this is all happening when you're doing this, you're doing A times the y, whatever the y is in your coordinate. It's a vertical action, so you multiply it times the y. Okay? And this one over here, E, this one that's outside, this is your vertical shift. So you're doing y plus e or y minus e, whatever it says to do, that's what you do. And you shift the points vertically, up and down. So those are your verticals. Inside, with the x, c represents what? It's horizontal because it's grouped with the x. So it's a dilation or it's a flip, right? But always remember to do the opposite, right? So you do your x divided by c. You do the opposite of what it says. So if it says times 2, divide by 2. If it says times half, you multiply times. If it says half x, then you multiply times 2, right? So it's take your x, divide it by c, whatever it is. And how about this last one right here? If it's minus d, what's that? Horizontal shift, right? So you do x minus d, right? So you do the opposite of what it says. If it says plus d, you subtract d. If it says minus d, you add d. So remember, your horizontal actions are always opposite. okay? And I'm not going to ask you to do multiples. You'll do either a stretch vertically or a stretch horizontally or a shift vertically or a shift horizontally for now. Okay? So I just wanted to remind you of those things. So let's do a couple of basic things. And let's try to remember to use our 3 sets of points. 1 over the base, -1, 1, 0, base 1. Those 3 points. So it says, sketch the graph of f of x if log base a of x of log base f of x equals log base a of x if a equals 2. So we will be graphing f of x equals log base 2 of x. First, domain. 0 to infinity. So that means I have a vertical asymptote of x equals 0. I can approach 0 equals x, but I have to break up my domain. I can only graph on the right side of the graph because x has to be greater than 0, so it's all over here on this side in the domain. Please label your vertical asymptote. Okay? And then we're going to pick the basic points. 1 over the base, -1, 1, 0, and base 1. You can either do that, or you have to convert this to 2 to the y equals x. If you want to put it in exponential form, just take the base, switch the x and the y. And if you're wondering how I did that so quickly, I will just show you. Y equals log base 2 to the x, and just converting it, 2 to the y equals x. Okay, if you're doing a table of values, you pick y, -1, 0, and 1. You do 2 to the y, so 2 to the -1, 2 to the 0, 2 to the positive 1, and you find x. So you work backwards, 1/2, 1, and 2. But I had already found those points, right? Yes. It's always going to follow that pattern. If there's no transformations, those are the 3 points you graph. So 1/2, -1, 1, 0, 2, 1. We'll do another one. 2 to the 2, y equals 2 is 4. So we give 4, 2 in there, just for fun. So there we have logarithm base 2. You guys do the next one. So with this one, you were using base 3, just the basic function. So 1 over 3, -1, 1, 0, 3, 1, graph them. It has the same domain, so we don't have to worry about a domain shift or a vertical asymptote shift. The last one is different because your base is less than 1. So when base is less than 1, your graph will fall instead of rise because it should be decreasing or decaying, just like with exponential decay. So with this one, we're doing f of x equals log base 1/2 of x. We're going to use the same set of points. And P.S. if you're going to convert that and do 1/2 to the y equals x, I'm okay with that. If you'd rather just do a table of values, just know I'm not doing a table of values. You've had a lot of practice. You don't need me to show you. I would do 1 over 1/2, -1, which is 2. And if you can't remember, 1 divided by 1/2 is the same as 1 times 2. Keep, change, flip. Then I would do 1, 0, and base, which is 1/2, 1. And those would be the 3 points that I would graph. So 2, -1, 1, 0, and 1/2, 1. And so your graph will decrease over the domain. Again, your domain hasn't moved. Every single time your domain is from 0 to infinity, so I haven't shifted the vertical asymptote at all. So let's make a generalization. If your base is greater than 1, what will your graph do over the interval of the domain? If your base is greater than 1, what does your graph do over the domain? It increases, it grows. If your base is less than 1 over the domain, your graph will decrease or decay. Okay? Same thing as it was with exponentials. Okay? All right, moving on. Now that we've graphed a couple of base functions without any transformations, we're going to look at a few. And I do want to change this A to be base, let's do base 5, just for fun. Base 5. So we're going to change it to 5 instead of 4, because your homework's full of A equals base 4. Okay? So we're going to be doing, I'm going to go ahead and just color code. So I'm going to make this one red. Of course, you can do whichever color you like. And I'll make this one blue. But here's the thing. I would really prefer to use my transformations and just graph f of x is equal to log base 5 of x and use the parent function without any transformation. So I can use those 3 points and then transform them using the values that I'm given. So I would say, first of all, that my domain, because it has to be positive, is 0 to infinity. So I would go in here, and I'm just going to do a dotted line for this graph because I wasn't really asked to graph the parent function, base log base 5. But I'm going to go ahead and graph it in so that I can use it to transform. So what points I want to do are 1 over the base, so 1/5, -1, 1, 0, and the base 5, 1. So you can see that that would be the parent function for of all log base 5s. Okay? And then let's take a look at what happens if we do log base 5 of -x. First, let's discuss the domain. Remember that our logs have to be 0 or have to be positive. So you say, all right, so -x has to be greater than 0. It has to be. Otherwise, it's not a solution. So if we divide by -1, so we can figure out what our domain is, x is less than 0. It's true? Right? Because we divided by a negative, so we have to reverse the inequality. So our domain is from -infinity to 0. So that means we have to graph to the left side of our vertical asymptote. It's still x equals 0, our asymptote. We're going to approach it, but now we're going to approach it from the left instead of from the right. Because what does this represent right here, this negative? What are we doing to our graph? This is a horizontal flip or reflection. So that means we're going to take all our x coordinates and we are going to multiply them times -1. That's what it means. Multiply times -1. So horizontal reflection. So let's take this point right here. X equals 1/3 times -1 is -1/3. So horizontal reflection. It flips to the other side of the vertical asymptote. 1. X equals 1. 1 times -1 is -1. Oh, that's 1/5. Sorry, 1/5. And then 5. 5 times -1 is -5. So the graph flips. Quickly, if you're going to use your table of values, of which I'm not going to create a table of values, but I will show you how to convert this. Your job is to isolate your log and solve for x. That's your job. If you're going to do the conversion and put it in exponential form and make a table of values. So your other option is to say, okay, y is equal to log base 5 of negative x. So my log's already isolated. So I'm going to convert 5 to the y equals negative x, and then solve for x. So I would divide by negative 1. So x is equal to negative 5 to the y. And then you just pick values for y, negative 1, 0, and 1. You do a negative 5 to the y power, and you'll find your x's. They will be the points that we just graphed. Okay? Questions? All right. Next one then. Let's look at our transformation of log base 5 of x. What does this say we're going to do? Horizontal shift right 1. So we're going to push all of the points right 1. So we're going to take this point and push it right 1. This point right 1. This point right 1. And regraph. You're just taking your x's and adding 1. That's what you're doing because it's a horizontal action. Right 1. So you take 1/5 and add 1. 1 and 1/5. 1 plus 1 is 2. 5 plus 1 is 6. Shift your x's to the right one. Again, with your conversion, that's 5 to the y equals x minus 1 if you convert. And then add 1, add 1. So that's 5 to the y plus 1 equals x. And that plus 1 is down here. So when you pick your values, again for y, you'd pick negative 1, 0, and 1. And you do 5 to the y plus 1. So 5 to the negative 1 plus 1. 1/5 plus 1 is 1 and 1/5. You'll see that it works out exactly like it just worked out on our transformation. One thing I did not mention, oops, I'm not perfect, is the domain shift. What's our domain restriction here? Yeah, x minus 1 has to be greater than 0, so x has to be greater than 1. So that does shift your vertical asymptote to x equals 1. So your asymptote also has to shift. So I'm sorry I forgot to mention that. Taught this lesson 5 times today, and that's the first time I forgot that. I'm on like autopilot, I gotta tell you. So x equals 1. So there you have some examples where you'll have to use some horizontal transformations. All right, last one, quickly. So it says sketch the graph of f if a equals half. And then if you look at this, and you look at this, you look at these two, and let's go ahead and put like half in there. Shh. The conversions of these are a little bit more annoying. These are both outside the x, so they're not vertical, they're not horizontal actions, they're vertical, right? There you have a vertical shift down 1. There you have a vertical stretch times 2, right? So again, I would graph instead y equals, I don't want to do this in my pencil, y equals log base half of x. So we would just then graph the points, if you recall, 1 over the base negative 1. So 1 over a half is 2. 2 negative 1, 1 0, and base 1. So I graph those points with my domain of 0 to infinity. So I'd get my horizontal asymptote, or vertical asymptote graphed. And then I would graph my 3 points, 2 negative 1, 1 0, half 1. I think I'll get 4 2 in there, just 4 negative 2 in there just for fun. Okay, so there's the parent function. the base function, log base half of x. And when we go to this one, we have log base half of x minus 1. That just means we're going to shift vertically down 1. So we're going to do our y coordinate minus 1, whatever our y is, minus 1. So in this case, our y is 1. 1 minus 1 is 0. 0 minus 1 is negative 1. Negative 1 minus 1 is negative 2. And this graph just shifts down 1. No domain change. Domain is still the same, so we don't have to do a shift on our vertical asymptote because we didn't horizontally shift anything. And then I'm going to do the conversion real quick for those of you that would prefer the conversion. This one's more difficult to do. So we have y equals log base half of x minus 1. So to do the conversion, I told you, isolate the log and then solve for x. So right now, is my log isolated? Yes or no? Is it isolated on the right side of the equation all by itself? No, so we have to move the 1. So y plus 1 equals log base half of x. And now I can solve for x. I can convert half to the y plus 1 equals x. Then when you pick your values, of course you would pick the y's that would zero this out. So what you would have to be thoughtful about your y's. What y's would you pick? Negative 1, because that would zero this out. So you would pick 1 to the left and 1 to the right. Right? If you're going to use your table of values, that's probably what you do. And then you're going to do half to the y plus 1 to get to your x. And again, I'm not going to fill that table of values out. You can do that if that's what you want to do. I really am trying to push you to use your transformations. They're more efficient. Okay? All right, here's the last one. What is this 2 telling us we're doing to the log base half of x? Vertical stretch. So that times 2. So we're taking all our y's and we're multiplying them times 2. All of our y's. So let's go over here to our parent function. What's my y right here? 1 times 2 is 2. Then I go to this point right here, 1, 0. My y is 0. 0 times 2 is 0. Then I take this point right here, 2, negative 1. My y is negative 1. Times 2 is negative 2. So this graph gets stretched vertically by a factor of 2. Because that's what it's telling us to do. If you choose, last one, to convert 2 log base half of x, first you have to isolate the log before you can convert it. So what would I do to isolate this logarithm because it's not isolated? Divide by 2. Absolutely. So y over 2 equals log base half of x, and then convert. So it'd be half to the y over 2 equals x. Now, I am going to give you all advice right now, because if I asked you to graph this, I would want you to be thoughtful about the points you pick for y. So if I wanted you to zero that out, y would have to be 0. Now, typically, we'll go 1 to the left of that and 1 to the right. But I don't want to do that, because if I do 1 to the left, if I do negative 1, don't write this down, just watch, I'm going to end up with 1/2 to the negative 1/2 power. That you have to think about. That's a pain. So here's my suggestion when you have a rational exponent, y over 2. Pick multiples of 2, numbers that are divisible by 2. So I would pick negative 2, because negative 2 divided by 2 is negative 1, and half to the negative 1 is 2. It's easy to do that math, and I would pick. So here's my advice for that if you wanted to make yourself a note. Pick multiples of your denominator to the left and to the right of your 0 for your exponent. Okay? So, again, no domain change there. Anyway, homework. Problem 33, A through G and I. And it's on homework 6.3 on Canvas. It's 8 graphs. If you want to do multiple graphs on the same set of coordinate axes, color code.